Hello and welcome to this video about diagonalizing matrices. In this video we'll be doing step 4, which is to find the eigenvectors of a matrix. We'll start off by defining the eigenvector storage type. It is an expansion of the frequency list type, which was discussed in step 3. These three attributes listed here were described in the last video. Number is equal to the total number of different eigenvalues found, and values were a list of these eigenvalues. And occurrence was the amount that each of these occurred. For example, if 5 was found twice, it would be listed as 5 in the values list, and have an occurrence of 2 in the occurrence list. The vectors attribute contains the eigenvectors that correspond to these eigenvalues. They may be stored as an independent variable pointing to a column in a matrix. And the occurrence of these eigenvectors is listed here. If an eigenvalue occurred twice, then it should have 2 eigenvectors that correspond to it, if it is diagonalizable. If only one eigenvector can be found for an eigenvalue that occurs twice, then generalized eigenvectors need to be found. There won't ever be more than 2 eigenvectors in this case. And here is a Boolean variable that is either true or false, or yes or no. If all of the eigenvectors can be found, then it is set to true or yes. If they can't all be found, then the matrix is not diagonalizable, and this attribute is set to false or no. So here's a bit of theory. This is the equation that is true for eigenvalues and their corresponding eigenvectors of a matrix A. Last time we found all of the eigenvalues, and we have to substitute them back into this matrix so as to find their corresponding eigenvectors. So the reduced row echelon form of this matrix will also equal 0 when multiplied by its corresponding eigenvector. This is because getting a matrix into reduced row echelon form is the same as multiplication by a matrix that is a product of all of the row operations required to reduce it to this form. So multiplying the 0 by this matrix on the right-hand side will cause the right-hand side to still be 0. So V is more precisely described by this equation. Since this is a 0 or null matrix, then V won't be only the 0 vector. V is really a member of the kernel or null space of this matrix, which contains an infinite number of vectors, but mostly vectors in the same direction or plane. And so combining these first two equations gives us this equation, and so we're in a good position to find all of the eigenvectors using this equation. Here is an example of a matrix that we're trying to find the eigenvectors of. So one of the eigenvalues is equal to 5. This is the 0 matrix corresponding to lambda is equal to 5, which we're trying to find the eigenvectors for. So this value of 5 is subtracted from the diagonal elements of this matrix. So after reducing it to reduced row echelon form, we get this matrix, which we can use to find the eigenvector corresponding to the eigenvalue of lambda is equal to 5. This eigenvector would be an element of the kernel or null space of this matrix, which would be an element of the kernel of this matrix in reduced row echelon form. So now we have to solve this equation to find the eigenvector. The solution to this equation may be thought of as a vector containing letters in alphabetical order descending down the list, and solving this equation. The kernel may be thought of as solving an equation for x times y is equal to 0. It looks strange because in this case neither x nor y is equal to 0, which couldn't happen with real or complex numbers. Expanding the left-hand side gives us this expression. We can extract these two equations from it. Both a and b can be expressed in terms of c. So v can be expressed as this vector, and the variable c can be factorized outside. And this is the eigenvector here, which we'll insert into the eigenvector data type. And now to check the solution to see if it is correct, and does produce 0 as a product when multiplied by this matrix. And so, evaluating this matrix product gives us this result. And we can eliminate all the zeros and simplify it a bit again. And so we get this vector which looks like it could be 0. And so it is 0. So this vector is an element of the kernel of this matrix. And so now it's time to make some observations about an eigenvector and what it looks like in terms of its corresponding matrix in reduced row echelon form. And so it looks like we've copied the contents of this last column, which doesn't contain a leading one, into the eigenvector, and then multiplied all of the numbers in it by -1. This isn't exactly true, as we'll see later, but it is true when all of the columns containing leading ones are next to each other, and none of the columns are completely 0, like it is here and for most matrices. And a number 1 gets inserted into the row of this eigenvector that's equal to the position of its corresponding column, and this is always true. It seems now that these values are purposely selected so as to cancel each other out, so that a 0 vector will result from their product. So let's see what is actually happening, and why a matrix multiplied by its eigenvector is the same as multiplying this vector by a scalar. We can separate the null matrix and the eigenvalue matrix here. And so this is equal to a null matrix plus a diagonal matrix together multiplied by this eigenvector. And so we expand the brackets. And so the first product is the 0 vector, because the eigenvector is in its kernel, as we calculated before. And the second product is equal to the multiplication of a vector by a scalar. And so multiplying this matrix by its eigenvector is the same as multiplying this eigenvector by its eigenvalue, which in this case is 5. And so here is another example of a matrix to find the eigenvectors for. This time there'll be 2 eigenvectors for this eigenvalue. So, just like the last time, we'll subtract the eigenvalue from the diagonal elements to give us the null matrix with a kernel that contains more than just the 0 vector. And then we'll have to reduce it to reduced row echelon form, which isn't the identity matrix and therefore must be a null matrix. And so the kernel of this null matrix is equal to the kernel of its row-reduced matrix, shown here. And so we set the problem out again so as to make it look neater. We'll have to find the kernel of this matrix. And the kernel is equal to this vector ABC, and we'll have to solve this system of equations to find it. And multiplying the matrix by this vector gives us this vector, which must equate to 0. And so we must take this equation out of this system of equations to solve on its own. And we can only eliminate one of these variables, namely a, because there's only one equation. If we had two equations, we'd be able to eliminate b as well. And so substituting this value in for a gives us this vector as the solution, and representing all of the vectors in the kernel of this matrix. And this can be expressed as these two vectors, multiplied by the independent variables, which are b and c. And so these are the two eigenvectors that we are looking for. And now, to check that this solution is correct, we only need to multiply the reduced matrix by this vector. And expanding it out gives us this vector. Notice how the different variables are going to cancel each other out. And we can eliminate all of the zeros in this vector. And doing some more simplification does this. And so we end up with 0 b's and 0 c's, which will give us 0 for any selection of b and c. So this vector is in the kernel. So now to make some observations of what the eigenvectors look like in terms of the row-reduced matrix, and see how to construct them. We get the information for the first eigenvector from this column. It looks like we're just copying out the column, but we're not doing that exactly. Next, we get the information from this column so as to construct this second eigenvector. Then, because we used the second column to get information for this eigenvector, we then place a 1 in its corresponding second row. And then, because we used the third column to get information for this second eigenvector, we then place a 1 in its corresponding third row. And then we place zeros in the remaining spaces to complete the eigenvectors. And so now it's time to look at a special 4x4 matrix example. And so now it's time to subtract the eigenvalue from the diagonal elements of this matrix to create its corresponding null matrix. And now to reduce it to reduced row echelon form. We can see here that the columns with leading ones are not next to each other, and this is important to show exactly how information is copied to the eigenvectors from each non-leading ones column. So now we have to calculate the kernel of this null matrix, which will be equal to that of its corresponding row-reduced matrix. So the kernel of this matrix will be equal to the eigenvectors of the 4x4 matrix example. The kernel will be equal to this vector a, b, c, d. We'll find it using the equation shown here. Multiplying this matrix and vector together gives us this equation. We can take these two equations out and solve them with real number algebra. Then we can eliminate two variables because there are two equations, leaving us with b and d. Substituting these values back into the vector gives us this vector, which is already a solution to the kernel. The variables b and d may be factored outside these two vectors like this. And so these are the eigenvectors that we're looking for. And now to check that these really are the eigenvectors, we need to check this vector by multiplying it by this matrix, like this. And so multiplying these two things gives us this vector, which contains 4 unsimplified expressions. And we can eliminate all of the zeros in this vector, which gives us this vector, which looks like it could simplify to become the 0 vector. And so it does. So this vector is a solution for the kernel. And so we've found the eigenvectors. So now to observe how eigenvectors are formed from this matrix. So this is how to get the first bit of information from this column into the first eigenvector. Because it meets up with this leading one in this column, it is copied into this row in this eigenvector. And similarly, this element is in the same row as this leading one. That's in the first column. And so it goes into this row in the second eigenvector. But notice this. This element is in the same row as this leading one. And the leading one is in the third column. And so it gets copied into the third row of this eigenvector. This is important, since it doesn't just get mindlessly copied into the second row, as it looks like it might be, since the leading one's columns are not next to each other. And so we got information for the first eigenvector from the second column. So a 1 gets put into this second row of this eigenvector. And likewise, because information was taken from the fourth column into this eigenvector, a 1 is placed in its fourth row. And then zeros are placed in the remaining positions of these eigenvectors. And so we finished finding them. And now to write some computer code to find the eigenvectors of a matrix. We firstly subtract the eigenvalues from the diagonal elements, and then reduce it to reduced row echelon form. The number of eigenvectors for this matrix may be found in a number of ways, but one way is to count the number of rows that contain only zeros. The number of columns with leading ones is equal to the number of rows in this matrix minus the number of eigenvectors. Notice that because these matrices are square matrices, the number of columns is equal to the number of rows. So this is how to write code to find all the positions of the leading ones in an array called leading ones. We start with a loop that will step through all of the columns containing leading ones. I is the counting variable for the row position. Here are two variables initially set to 0. J is the counting variable for the column position. EL is the value of the element found at position ij in this matrix and is initially set to 0, so it can enter the while loop. We'll keep looping through the column positions and get the value of this element at this position until it is equal to 1. It should be equal to 0 until it is finally equal to 1, and then this should be the leading one. And this section tells the computer to keep incrementing the column position until it gets to a position where the element is equal to 1, so this would be the leading one. After it has found this position for the leading one, it copies it into this array. And so the leading one array should look like this for this matrix. And now to write code to find the columns that contain information for the eigenvectors. we set x1, which is equal to the location of the first column of leading ones, to be equal to 0 to start with. And we also must reset the eigenvector column counter k to 0. And now to loop through all of the list containing the positions of the leading 1 columns. So we get the value of x2, which is the location of the second column, containing leading 1s, which is the larger number. In the case where there aren't any more columns with leading 1s left, and there's still some columns left, then set this value of x2 equal to the number of columns plus 1, so as to capture all of these eigenvector columns. Now we loop between these two columns containing leading 1s to get all of the columns in between, which are eigenvalue columns, and put all of the numbers of these columns into the eigenvector columns list, and increment the eigenvector column counter variable k, and then pass the value of the leading 1s column down from x2 to x1 so that it will become the lower bound after it has been the upper bound. And this is what the eigenvector column array should look like in this example. And so now it's time to calculate the eigenvectors for this matrix. The eigenvectors should be set to 0 from the beginning, so that any elements in the eigenvectors that are not set during the process of calculating them will already be set to 0. So now to write code to find the eigenvectors. We loop through all of the eigenvector column positions in the matrix. We get the next column to read, which is called col I. We then loop through every row of each eigenvector column. We then get the next leading 1 column. And then we copy information from this eigenvector column into the eigenvector. And then we place a 1 in the appropriate position in each eigenvector. And the other values have already been set to 0 from earlier in this code. And now to look at a matrix with letters for elements, so as to see how it behaves, and get some sort of feel for how a kernel is constructed and how it works. And multiplying the vector by the matrix gives us this vector. We can take these equations out of the vector and solve them so as to eliminate 2 of the variables. And so we get this solution for the kernel. And if we factor out the independent variable, we end up with this vector. This is also an eigenvector of this matrix. So to check if it is a solution, we substitute it back into this equation. It also helps us to see why it is a solution. I've coloured in the different elements so as to be able to track them in the calculations. And multiplying these two entities together gives us this vector. Can you see how they are multiplying together so as to make 0? The vector was constructed so as to cancel out the x's and y's, so as to eventually give an answer of 0. And so simplifying these vector elements gives us this, which obviously should give us 0. And so it does. So this vector is in the kernel of this matrix, and any multiple of it should be in the kernel too. And so it gives us the entire kernel. And so here is another example of a matrix with letters for elements, and which has 2 eigenvectors. The kernel has already been calculated and is now to be tested. It is also a good example so as to observe how kernels are constructed and how they work. You can see how the different elements have been multiplied together so as to give an answer of 0. And simplifying these numbers gives us a 0 vector. Can you see how the elements of a kernel vector multiply together with its corresponding matrix so as to cancel each other out and so give a 0 vector? And here's an example of a 4x4 matrix that is similar to the one given in the example. We're going to multiply it by its kernel vector and see how the different elements multiply together so as to cancel each other out and so as to make the 0 vector. Here we have two expressions that are going to be equal to 0. Can you tell which elements have been multiplied together? And so simplifying these expressions gives us this 0 vector. So I hope that this video has been helpful for you in your quest to find and understand eigenvectors, and also to write computer code to find them.